Hello, I'm David. I'm the coordinator of the Maths Learning Centre, and this is a revision seminar for Real Analysis 2. It's semester 2, 2021. If you're watching this in the future, hello from the past. I really hope it's much nicer there. We've had a rough trot in the last couple of years, but we're doing okay because we're doing real analysis, and that's lots of fun. And so here we are. I've been given a heap of requests. And I will do my best to talk about them. And so I'm going to start with countability. Just remind you of the rules in a revision seminar. It's your seminar. Please ask questions or make comments about how you're feeling or what you're thinking about things. That's really important to me. If I write something on the page that is patently wrong, please tell me immediately. Do not wait for me to finish the sentence, just tell me. If I say something that you're wondering about and it sparks a question in you, maybe wait till I finish the sentence and then ask. So if you're in the Zoom, just use the chat or turn your mic on and just ask. If you're in person, then wave at me. Yeah, that's basically it. And I will attempt to remember to stop every 5 or 10 minutes and give you a chance to say things. Yeah, cool. Countability. So just want to check, why is countability in this course? And I think it's because this course is about what the real numbers are. And the real numbers are an uncountable set, and so that's why we care about it. But there's 3 axioms that define being the real numbers. Is it's a complete ordered field, and you can't be complete and ordered without being infinite. Yeah, so there are plenty of finite fields, but they are not ordered and they're not complete. And there are infinite fields that are ordered but aren't complete, which is like the rational numbers. So the rational numbers are ordered but they're not complete. And the complex numbers are a field and they're complete but not ordered, because you can't figure out, for example, what order I and minus I are in. They're sort of the same length. And R is in between, and it is both, it is a field and it is complete and it's ordered. And you can't be both complete and ordered without being uncountable. And there you go. Okay. But also countability is important for the perspective of making sequences as well. And sequences are one of the big ideas in real analysis as well. So this isn't about countability yet. It was just the first thing that popped into my head. So that's what I'm saying. But I really like that the posters on the wall of the Maths Learning Centre that say NZQRC, that the last 3 are an ordered but not complete field, a complete ordered field, and an unordered but complete field, which is 3 of the options. The only other option is neither ordered nor complete, and that all finite fields are of that type. Anyway, that just appeals to me. So when I've been in the Maths Learning Centre with real analysis students, I can point at the wall and talk about this stuff. Okay, so countability is a different thing that you can talk about with a set of things. We're going to talk set of numbers, it's about the sizes of sets. And so some sets are finite and you can count how many things there are, and many sets are infinite. And there are at least 2 levels of infinity. And one of them is countable. So there's finite, and then there's 2 levels of infinite. And the first level of infinite is countable. and the second level of infinite is uncountable. And technically finite things are countable as well. So there's countable infinite, but this is basically it. So this is sort of in order of size goes this way, where size I define to be sort of undefined. But uncountable sets are bigger in some sense than countable sets. In as many senses as you desire, they are bigger than countable sets. So the very first size of infinity is the size of the natural numbers, and that's the countable sets. The natural numbers. Can I ask, does your lecture include 0 in the natural numbers? No? Okay. It's different in different courses, so worth checking. So anything that is the same size as the natural numbers is a countable infinite set. All countable sets are the same, countable infinite sets are the same size as the natural numbers. Yep.
Same size. One example that lecture was that like 2n, where
yes, I will talk about that. But it's a very important thing. I'm going to say relate that to the people who are listening online and who didn't hear it. The even numbers, the even natural numbers, 2 times n, are clearly less of them than the natural numbers, because it's only half the natural numbers. But in the sense of this, they are the same size. And so that's why size is such a weird ass concept. So we define being the same size, and we don't use the word size. I believe the official word is cardinality. You define being the same cardinality. I'm just going to check that. Oh, equinumerous. But you define having the same cardinality as there being a one-to-one and onto function between them, bijection. That's what we define being the same size as. So same size, that's what I think of it in my head. And there's like cardinality is the fancy word we use for size because we don't want to use size because it's too unfancy. The same cardinality, it means there is a bijection between them. And by bijection, we mean a function that goes from one to the other that covers everything in the second one and only covers everything in the second one once. So yeah, it's a surjection. Sur is French for on, and which means it's onto everything, covers all the things, and it's an injection. I don't know why in, meaning it doesn't cover anything more than once either. So that the definition of countable means that it is possible to find a function from the natural numbers to your set that covers the entire set and doesn't cover anything more than once. I'll do that. That function from, not that function. Just a second. So this function is going to send the natural numbers to the integers. Okay? I mean, you can send real numbers to real numbers as well, but it sends the natural numbers to the integers. And f of 1 is 1 squared minus 5, which is -4. And f of 2 is 2 squared minus 5, which is -1. And f of 3 is 3 squared minus 5, which is +4. And I haven't done what I was hoping for, but that's okay. All right, let me just think of another one. No, 2x is 1 to 1. Like it is. I'm trying to say it doesn't cover anything more than once. Just give me a second. I really thought that would work. I don't want a 5 then. I want a square number. It's not going to work for Z to N, but for Z to Z, it doesn't work. So I'll do that. This is the problem of not being able to prepare. So if I have x squared going from Z to Z, like, or maybe from, I know that these are the same function to the same set twice, but just bear with me. Or even from Z to R, then f of -1 is -1 squared, which is 1, but f of 1 is also 1. And so this number 1 has been covered twice by the answers from the function. That's what I mean by being covered twice. So this function isn't injective because it's possible to produce the same output from different inputs. The definition of injective, I don't know what it is in your course, but there's two definitions. One is that every input produces a different output from every other input. So that if x1 is not equal to x2, then f of x1 is not equal to f of x2. That's injective. Or it could be that if two outputs are the same, then the inputs have to be the same. The only way to produce the same output is to produce the same input. Yeah. So this is what one-to-one means in a natural sense. Like all the inputs produce different outputs, but this is the easiest one to prove in a proof. Yep. They are totally equivalent, contrapositive. They're the contrapositive, but they feel different to a human being. So, yeah. So we choose this one as the definition, even though they're equivalent, we choose this one as the definition because it's easier to run a proof beginning with this and ending with this. Because it's much easier to talk about things being equal than to talk about things being not equal. So, yeah. So, if I want to decide if things are countable, I have to just wait. So if you're going to have a function from, it doesn't matter which way the function, it's a bijection, so I could do it backwards if I wanted. Like bijections are invertible, I can do them backwards. So if instead of thinking of it as being in a bijection from the natural numbers to your function, you could do it the other way, to your set. You could do it the other way. So if you've got a set and you have a function that takes all these numbers or objects to the natural numbers, one of them will go to 1 because it's a bijection. It has to produce 1 somewhere, and one of them will go to 2, and one of them will go to 3, and one of them will go to 4, and one of them will go to 5. This is exactly what you do when you count things. You point at them and you say numbers. That's why it's called countable. Right. Because you're literally counting them when you create this function. Yeah, that's why. So if it's possible to put them in order one at a time and still cover them all, then they're countable. And so the proof that the rational numbers are countable basically runs by saying, I'm going to put the rational numbers in order. Not in the size order, because if you're in size order, any two of them, they can find another one in between, but in a different order that covers them all. And so Q could be set up as, let's run through all the fractions which in their lowest form have the numerator and the denominator add up to 1. And so I'll go 0 over 1, add up to 1. And then I'll have the ones where the numerator and the denominator add up to 2. So this is just the positive rational numbers. And then this one, I'll have 1 over 1, that's good. The numerator and the denominator add up to 2, that's good. And then I could have also 0 over 2, but we've already covered that, so we don't need that one. And 2 over 0 doesn't exist, and so the next one we could do 2 over 1, and we could also do 1 over 2. And I'll just put them in order based on what the numerator and denominator add up to, and then use the biggest numerators first. And this will create a list that will produce all the positive fractions. And therefore it's countable. Yep.
Yeah, so because we're making a bijection with this, there's no issue with writing a 0 over 2 and crossing it out. Because like,
Yeah, I just choose that's not there.
yeah.
Yeah. This is my bijection. This is number 1 and this is number 2. I didn't have that one, so it doesn't matter. And this is number 3 and this is number 4. It doesn't have to be a formula that does the bijection. It can just be a list.
Yeah.
Yep.
It's like we're trying to prove a certain set of something like this.
You just have to be convincing that it covers all of them. And most people do that this way, where this is the numerator and this is the denominator. And then you go 0 over 1, that's this one here. And then 1 over 1 is this one here. And 2 over 1 is this one here. And then 1 over 2 is this one here. And then you end up having this zigzag that covers them all. Yeah. And I know that some of them are represented in this grid twice, but you just ignore the later ones. So, and that's enough. You don't even need it to be a bijection technically, because if there's just a if there's just an injection that goes to the natural numbers, then your set has to be countable. So if you have all of your things produce a natural number as the answer, and there's some natural numbers missing, well, that's okay, because the size is less than the natural numbers, or equal to.
It doesn't need to be a bijection.
No, it just needs to be like, if you've got your function going from the set to the natural numbers, an injection will make it countable or finite. The set is countable or finite. And if you have f going from the natural numbers to your set, and if it's a surjection, then your set is countable or finite. So the idea being that here's your set, and it produces the natural numbers, and maybe it skips four and produces 5, but the fact that it doesn't produce all the natural numbers just means that the size, it's less than or equal to the natural numbers, so the size has to be finite or countable. Yeah, but it's safer to just make a bijection if you want it to be countable. And it's really hard to prove that things are uncountable. Like, there is a proof in here, and the lecturer said this is more elementary than the diagonal argument with whatever. And I say, well, sure, for the sense of elementary, which means not using any axioms that aren't listed here, but not more elementary in the sense of easier. So yeah, it takes some serious work to prove that things are uncountable. And you have to do it by contradiction usually, because it's not something else. Yeah. But in a general sense, it's okay to just know some things that are definitely countable and uncountable. Like N is countable, Z is countable, Q is countable, R is uncountable, and C is uncountable. Because R contains C, so it has to be uncountable. So these are countable, and these are uncountable. And yeah. And there should be some exercises, right, that go with choosing if things are countable. Meh, I can't see them. Yeah, okay. So to show two things of the same size, you need to set up a thing for them. So for example, there's an exercise in here that says show R and R without 0 are equinumerous. which is in general true for any infinite set, and removing one number will still be equinumerous. Means you need to set up a function that is one-to-one and onto, like surjective and injective, that goes between those two things.
There's a practice exercise here that set is.
Sure.
So it's just set all infinite sequences.
Okay. So prove the set of infinite sequences of zeros over ones is uncountable. Okay, so let me just understand what these things are. There's one that's all zeros, and there's one that's got a 1 and then all zeros, and then there's 0, 1 and then all zeros, and there's 1, 1 and then all zeros, and then there's 0, 0, 1 and then all zeros, and 0, 1, 1 and then all zeros, and then 1, 1, 1 and then all zeros, and 1, 0, 1, and that sort of thing. And then there'd be ones that'll have all ones at the end as well, and all of those things. Okay, so like basically decimals, right? If I put a 0 in front of here, they'd be real numbers, yeah? Not that this is a thing, but I'm just thinking it through. Okay, sweet. So to prove that that set is uncountable, I would have to show that it's impossible to list them all. Like this list that I'm doing here, and I'm being very systematic about it, I'd have to show it's impossible to include everything in a systematic list. Because if I could, then it would be, this would be number 1, this would be number 2, and this would be number 4, and I'd be counting them. Okay. Cool. And to show that something's impossible is very hard. And so what you normally do is you pretend it's possible and find something that is bad. So I would do it by contradiction. So just making sense of myself. So I reckon that I would go suppose it's countable, blah, blah, blah. I don't know how long it's going to take. And at the bottom, there'll be contradiction, therefore it's uncountable. That's my proof. Okay. Always good to have a plan for how it's going to be structured. And it seems to me that if it was countable, I could do this. So if it was countable, or if I'm going to use a subjunctive mood, if it were countable, then it would be a bijection between it and the natural numbers. Yep. So suppose it is countable. All right, I don't need to do that. Then there is a bijection between this set and n. So the set can be written in order, with the one that goes with 1 first and the one that goes with 2 next and whatever. Okay, so let A11, A12, A13, etc. be the first one. And A21, A22, A23 be the second. And AN1, AN2, etc. be the nth. Okay, and so there's my list. It's like this. So now I want to show that I haven't actually covered them all after all. Which means there has to be a sequence of zeros and ones that is not in this list. And so what I'm going to do is I'm going to make one that is guaranteed to be different to all these things. So I'm going to choose B11 to be equal to 0 if A11 is 1 and 1 if A11 is 0. So it's definitely different to whatever A11 is. So no, just B1, sorry, not 1, 1. And then B2 will be 0 if A22 is 1 and 1 if A22 is 0, and so on forever. And then this sequence, B1, B2, B3, etc., is not A1, 1, A1, 2, etc., since the first terms are different. And similarly, B1, B2, B3 is not AN1, AN2, etc. for any n. And so the list does not contain the whole of the set. Contradiction. Yes, it's two implication signs pointing at each other with a wall between them. So, contradiction. And therefore, the set is uncountable. Probably would have been better if I had given this sequence a name, like this is sequence A1. That's traditionally how you write a sequence with the round brackets, is that right? Yeah. And A2 is this, and so on. Then it would have been easier to say that the sequence B is not equal to the sequence A1, something like that. This is Cantor's diagonal argument. I can't use the proof that was in the notes for proving that the real numbers are uncountable because it uses the fact that the real numbers have an order, like are sets of numbers that come in an order. Like you use intervals of numbers to do that, don't you? Yeah. Like you make nested subsets, right? So the proof in the notes that the real numbers are uncountable uses intervals, which is a property of the number line, whereas this set is not made of numbers, it's made of sequences of zeros and ones, and so they don't have a greater than or less than relationship, and so I can't use this sort of idea. So yeah, so as much as he said you may have seen a proof that using the decimal expansions, we have to use that proof for this because these are sequences of numbers. So yeah, so I happen to know this proof already, but I was trying to set up how you might think of it if you were aiming to do this. So you'd set up, go, well, being countable means you can put it in an order. And if it's not countable, there must be something that isn't in this list. I haven't covered everything. Yeah. So no matter what list you choose, there's always another one. Yeah. Even if I put the one that I found in the list, I could do it again. How do people feel about what just happened there?
It's to set up as generally as possible and then try and find some of the breaks.
Yeah.
And so this method handles I1.
Yep.
Yeah, so that is just the normal quantity is always there.
I don't know, but this is the one that I would use for sequences.
Okay.
So this Cantor's diagonal argument is normally used to prove that the real numbers are uncountable, or at least the space between 0 and 1, because you have 0 point and then you've got a sequence of digits and you just choose your number so it's different in each position. And I was just modifying it. And it's not a bad thing to find a proof you've seen before and modify it for the situation you're in. Yeah, so your lecturer is, obviously you can't do it in your exam, but your lecturer is expecting in your assignments for you to go looking and say, well, this proof's not that different, I'm going to modify it. Yeah. But other things, now, well, I did have an exercise there that was to show that R and R without 0 are equinumerous. That's how I would write it. The size of R is the same as the size of R without 0, but R and R without 0 are equinumerous. which is basically showing that this set is uncountable because we know this one isn't. So I would, to do that, I would need to find a one-to-one and onto function between them, a bijection. So a function that takes the whole real line and produces as its answers all the real numbers except 0. Sorry?
Some kind of like asymptotic function.
Possibly. Something that asymptote sounds not unreasonable. Like 1 over x doesn't work because you can't put 0 in. It doesn't produce 0 out, but it can't put 0 in either. The other option is to say something that only takes in things that aren't 0 and still manages to produce the entire of the real numbers. Like ln of the absolute value of x does that, but it covers everything twice. Yeah. Okay. So if I was going to prove that the natural numbers were the same size as the natural numbers without 0, I'd just shift everything over by 1. But it's not like there's something that's next to 0 that you can shift over, because you can be as close to 0 as you want. Yeah. There is one, and I hate these proofs because you have to just think of something. But I'm just, the graph would be like, the domain is this, and the range is this. Like, so it's not allowed to produce 0, but it has to be able to produce anything as close to 0 as 1. So something that does this would be nice. That's great, but it doesn't work for, I can't put 0 in. Anyone in the Zoom got any thoughts? And do we know what the lecturer thinks that their answer is? So you had like y equals x, that's what you were saying. And you want to not have this, but still somehow cover it. Oh yeah, we'll just shift everything over like you said. Ready? Here we go. We're going to make this number 1 come out to 0. And number 2 come out to 1. And number 3 is going to come out to 2, like that. And so when I do the range, I get, oh, I've done it the wrong way around, but that's okay. The domain is everything except 0, right? That's my domain. And my range is, I actually did produce 0 because I produced it over here, and I actually did produce 1 because I produced it over here, and I actually did produce 2 because I produced it over here. So it's like f of x is equal to x if x is not in the natural numbers. Yep. And it's equal to x minus 1 if x is in the natural numbers. That'll do it. Nope, natural numbers. Because I only need to move down to cover the 0. I don't have to cover everything. And so, just to be sure that this really is onto, I know definitely it produces every non-natural number because it's x. So if y is not in the natural numbers, then y is already equal to f of y, so that's good. So that's onto for that. And I want to know if it is a natural number, if I can produce it. If y is in the natural numbers, then y is equal to f of y plus 1. And if y is, oh no, just crap. This isn't true for 0 because this is a function that takes r without 0 to r, because I didn't have 0 as an option here. And so I also need, if y is equal to 0, f of 1 equals 0. So that works. Okay, so it covers every real number, and we'd have to show it's 1-to-1 as well, but this graph satisfies the vertical line test, so yay. I don't know if you're allowed to use that in real analysis. Every vertical line hits this once, so it's a one-to-one function. But I could do it. Yeah, so if the result is a natural number or 0, then it can only have come from a natural number because of the way the definition works. This is a pretty bad example in terms of my rigorousness of the description of why. But yeah, I would need to make it more rigorous than that. But your idea was the idea that did it. I had to shift everything over by 1, but I couldn't shift the whole real numbers over by 1. But what I could do is just shift the natural numbers over by 1 and leave the rest of them where they are, and that works fine. So that was cool. This may not be the canonical answer, but it's an answer. Yeah. Oh, I just said it wasn't. Yep.
It just said because R without 0 is like that's a subset of R without quotients, which we know is unpractical. Yeah, but they don't have to assume that R without Q is.
Oh, okay. Yeah. Well, I mean, if you really wanted to do that, so you're saying, just want to make sure I understand that argument. You're saying that Q is countable.
Yeah.
And R is uncountable.
Yeah.
Therefore, R without Q is uncountable. Yeah.
Yeah. Well, we proved it like so I don't know if we can like take it as given.
And well, no, just a second. It doesn't work because R without 0 is just contained in this. It could be countable. Yeah. Oh, you're right. R without Q is contained in, and technically not equal to, but you know, is contained in R without 0. Yep. Because Q is in 0 is in Q, and so therefore, since this is uncountable, so is that.
Yeah.
Okay. That's an argument that works too, because this set contains that set, therefore its cardinality must be bigger. Yeah. Or equal. And since it's contained in R, and this is uncountable, and this is uncountable, therefore this is 2. It's the squeeze theorem for countability. Not that that's a thing, please don't say that in your exam. Yeah.
So this argument with like R without Q uncountable, does that work for any arbitrary sets like A and B? A is uncountable.
If A is uncountable and B is countable, and you remove, like if B is contained in A and this is countable and this is uncountable, then therefore A without B is uncountable. And you can probably prove that because if A without B was countable, then A would have to be countable.
Oh, yeah.
Because you could create your function as alternating between B and A without B. So that's the proof. If we want to prove that, suppose A without B is countable, then there's a function that goes from B to N, and there's another function that goes from A without B to N, which are both injective, no, bijective. And then you can create a new function which alternates between them. And so you can create a function. Oh, can I go from N to? No, that's not true. Yeah, you can list them in order, basically. The elements of F of B are B1, B2, B3, etc. And the elements of A without B will be like A1, A2, A3, etc. And so then the elements of B union A without B could be B1, A1, B2, A2, B3, A3, etc. And that lists them all once each. And so therefore B union A without B is countable. But B union with AB is A, which means A is countable, which is a contradiction because it was uncountable in the original thing. I like this, making a list. It's much easier than defining a function. So, yeah. Cool. Sorry? What's that? No, I really want to stop there because we've been going for like a while. Okay. If that's okay. I'm going to have a look at these sequences. No, not sequences, series. Sorry, that's not what I wanted. Series. And what I'm going to do is I'm going to have a quick look through the book and find all the theorems that tell you when a series converges. So I'm not actually going to cover all series, just series convergence. Yeah. Okay, so the definition of converging is the first rule for converging. So when the sequence of partial sums, which is this sequence, is that how your lecturer writes it when they want to specify what the ends are? This is the sum from a 1 up to a particular number. So this sequence of partial sums, and I'll just write it as a sequence. A1, A1 plus A2, A1 plus A2 plus A3, A1 plus A2 plus A3 plus A4. That sequence converges as a sequence. So a series converges if the sequence of partial sums, and I call this the sequence of running totals. You're doing a running total of what the terms of the sequence add up to so far. That sequence of running totals, if that converges, that is the definition of what this infinite series converging means. Yep, the actual definition. It's always something you can do. If, you know, anyway, hard to tell sometimes, but that's the definition. So the definition is what proves that the geometric series converges. No, just converges. Okay. Yes. So this is really important.
Do we go into that and prove there, or
No, that's a whole other thing, but that's another theorem that we'll use. But this is our first one. And what I was meaning by my capital N is that this one is the sum from n equals 1 to 1 of an, and this one is the sum from n equals 1 to 2 of an, and this one is the sum from n equals 1 to 3 of an. And so the sequence itself is made of n equals 1 to some number where capital N is the thing that's indexing this sequence. Yeah. And whatever that thing it converges to is called the sum of this thing. But this is the rule for whether it converges. This allows us to prove that geometric series converge when the number that in the power is number that's in the base of the power is less than 1. This is the actual definition. So just as an example. Prove that the geometric series n equals 1 to infinity of x to the n converges when the size of x is less than 1. And so we say this is the nth partial sum, you know, let Sn be the nth partial sum. I'm going to start at 0 if that's okay. You don't have to start at 1. Just make it easier for myself. So S0 is x to the 0, which is 1, and S1 is x to the 0 plus x to the 1, which is 1 plus x, and so on. And then there's some algebra that says that this is the same as 1 minus x to the n plus 1 over 1 minus x. Because algebra. But if you really want me to prove it, x times Sn is x plus x squared plus x to the n plus 1. And if I do this minus that, then these bits in the middle will cancel each other out. And I'll get Sn minus x lots of Sn equals 1 minus x to the n plus 1. Because this has got an x, and I'll subtract an x squared, I'll subtract an x to the n, I'll subtract an x to the n. And so Sn. So this bit here that I'm doing is in inverted commas just algebra and is not actually technically part of the real analysis per se. And so this converges when this sequence converges. And the limit as n goes to infinity of 1 minus x to the n plus 1 over 1 minus x equals 1 minus is that because of the limit laws? Because x isn't the thing that the limit is acting on, it's the number n, and so I can bring limits inside fractions and stuff. And this limit only exists if the size of x is less than 1, because otherwise it just gets bigger and bigger and bigger. So if x is like the number 1.3, then 1.3 to the power of 15 is actually quite a big number. 0 if x is less than 1 and does not exist otherwise. Oh, well, technically it's 1 if x is equal to 1. If x is equal to 1, I'm dividing by 0, which is a bit crap. So therefore, converges when the absolute value of x is less than 1. Because the limit exists when the absolute value of x is less than 1, therefore the original series converges when the absolute value of x is less than 1. So this is the only one I know off the top of my head that uses the actual definition of what it means to converge by creating a sequence of the things that happen from the partial sums. How are we feeling?
I mean, like, yeah, it's like you read all and like, yeah, that's cool. It's just like getting that first step.
Yeah, so what I would just say is that this is the only one I know uses this rule.
Yeah.
So if someone asks you to prove the geometric series converges at that time, this is the proof. And so it's one that you just have to know. I love this move. This is the coolest move ever, just here. It's just fabulous.
Yeah.
And- sorry? Yeah. And it's the same move you use to find the fraction version of a repeating decimal. The similar sort of move where you shift it over by 1 and then subtract, and then everything cancels out in the middle. Yeah. But I just wanted to show that that's a thing. I don't know if you're supposed to remember that proof, but if it turns up in your exam, I will feel extremely well justified. Yeah, but usually we don't go to that much effort. But you could imagine, an exam question that said, suppose AN, that went like this. Such that this. Suppose AN was a sequence, is a series such that the sum of the first n terms with n squared plus 1 over n minus 1. Does it converge? The answer is no, because the partial sums don't converge either. So it doesn't converge. Just like you could make up a random question that didn't technically require you to do anything, but used this fact. So. And that act of trying to make up how would I make up a question that got me to do this without me having to just randomly guess? Well, it mentions the partial sums, so that's what I'll use. Yeah. And series whose sequences are defined recursively might work that way too. So if you've got a sequence that's defined recursively where AN is defined using AN minus 1, then it might turn out that this is a useful strategy as well. But I'm not 100% sure. Oh, the third revision seminar is going to be fun. Oh, I have some water. Okay. And the answer is no, since partial sums don't converge. The sequence of partial sums doesn't converge. All right, and you'll probably have to say the limit of this doesn't exist, therefore no, it doesn't converge because the sequence of partial sums doesn't. Right, that's the first one we found. Our next on the list after that, that's the definition. We've got a theorem that says that if you've got two ones that do converge, then you can create new ones. Okay, so or CAN. Okay, cool. So convergent series are a subspace of the vector space of series, if you like. Because when you add them, it's still convergent, and when you multiply them by a scalar, it's still convergent. So it's yeah, anyway. Yay. Okay. All right. So that's fine. So that's only useful if you can look at it and know that it's made out of other bits that you know how to know that they converge. So that's not useful unless you already know things that do converge, sadly. Okay. The next thing that's said in the notes is that we can adjust this a bit by saying that actually by the that if your sequence is made of, if the sequence of ANs is positive, then the sequence of partial sums will also be positive, and will be increasing. And so therefore, so if all these numbers are positive, you can't add more and more positive numbers and make it decrease. And so if all these A's are positive, then this sequence is increasing. And so all you need is for it to be bounded above, and that will make it converge. Because an increasing sequence bound above converges. And so we could have, in this proof, when we got to this point here, go, well, if the size of X is less than 1, then this will keep getting smaller and smaller. And so it'll be bounded above. Right, yeah. So like this is less than 1 over 1 minus X. All right. So we've just added that if AN is greater than or equal to 0, then AN n equals 1 to infinity converges if this sequence A1 up to AN is bounded above. I don't know how that is useful, but I mean, I feel like it's slightly shorter than actually finding the limit. I feel like there's going to be a list of ones that only apply when the terms of, when the things inside the sum are positive. Yep. Well, the monotone convergence theorem belongs to sequences.
Oh, right.
And we're applying the monotone convergence to the sequence of partial sums and therefore ratcheting it into the series. Yeah. But basically this says that you don't need the ANs to be in any particular, they don't need to be growing or shrinking. They just need to be positive. And then if the sequence of partial sums is bounded, then it's automatically monotone convergence. So yeah, but the thing you mentioned should be here somewhere. Okay, so the next thing is a proposition that says that if it converges, then the individual terms that are being added, not the sequence of partial sums, but these things will have to go to 0. And that's the thing you mentioned earlier. This doesn't sound, this isn't at the moment written as if it is a convergence test. It doesn't say if this, then it converges or diverges. To write it as a convergence test, you need to say if AN does not go to 0, then this does not converge. That's the contrapositive. But this is the test, right? If the individual ANs, so if you've got a sequence of A1, A2, A3, etc., and then you've got a running total, you know, A and then this, which is what the thing is. The individual bits that you're adding on don't get smaller, then the running total's not going to, just going to keep getting bigger and bigger and it won't go anywhere. That's basically the theorem.
The convergence test should end with if something, then it converges, not if it converges with something.
Yeah, because if you want to use it to conclude whether it converges, it has to end with that.
Yeah.
I mean, it doesn't have to, but just like for the purposes of being a human who wants to use it to make a conclusion, then it needs to end with that. Yeah, so this is the theorem, the proposition, and this is the thing that I'm able to use to make a conclusion. So this thing never concludes that something converges. It only ever concludes that something doesn't converge. If these terms do go to 0, it might converge. It has a chance of converging. Not that there's probability about it, it either does or it doesn't, but you know, there is a chance that I'll be able to show that it converges if these terms do go to 0, but it won't be guaranteed that I'll be able to do that. Yeah. So far, these are all things that were in Maths 1B, technically. So next one we have is the geometric series. And so this is our first series that we know converges without having to prove it. Unless you're specifically asked to prove the geometric series converges, you are now allowed to just do it. So our list of series. The sum from n equals 0 to infinity of x to the power of n is 1 over 1 minus x. Your lecturer calls it r, but you know I'm used to calling it x. So, but only when the absolute value of x is less than 1. Otherwise, it doesn't converge at all. So I'm going to do the long version. It's like this thing doesn't converge if the absolute value of x is greater than or equal to 1. 0 to infinity x to the n does not converge if the absolute value of x is greater than or equal to 1. So this is our first known series. Unless you are specifically asked to prove the geometric series converges, in which case you'd have to do the other proof, then you're allowed to just use the fact that it definitely does. So that means that now you're able to use something like this and say, well, you know how it starts with if these two things converge, then this one does too. Cool, if you've got a series and it's made of geometric series, then you'll know that it converges or doesn't. Well, at least you'll know it converges. You usually won't know if it doesn't, because it does. This theorem doesn't say anything about this not converging. It finishes with these things converge. So you can't use this theorem to conclude that things don't converge. Yeah. But you do know that if this converges, then at least one of these has to not, because if they both did, then it would too. So that's a contrapositive. So, yeah. I'm doing well. No, we've got another test now. I'm going to put this on a separate list. That's our list of series that we know. The next test is the first one that's not in Maths 1B, and it's called the comparison test. So far, things haven't had names yet. This is the first one that has a name other than the definition of convergence. Some places in the world call this the divergence test, because it's pretty much, it's one of the only, yeah, because that's all it can tell you, whether it diverges. So the comparison test says that if Bn converges, the sum of Bn converges, so does the sum of An. And if the sum of An diverges, so does the sum of Bn. So basically, I can't read this and know what it's doing, but I can read this. If Bn is bigger than An and this one diverges, this is bigger, so it's going to have to diverge too. And if this is converges, then this is smaller, so it's going to have to converge too. It's sort of like it's like the sizes of sets, right? If a set is if you've got an uncountable set and another set that contains it, this is uncountable as well. It's the same idea. Not really, but it's a similar idea. So this is the first one. But again, this requires me to know the status of one of these series so that it can pass on to the other one. Which means you need to know series that do converge. Right. Let's see if we can do any of the problems now with what we've got so far. Oh crap, I missed a series. It's at the top of this page. The harmonic series. I think we get the one over as well. Yep, that's just here. This one doesn't have a name, sadly. So our list of series that we definitely know converge is now here. I'm still getting used to not having the things on the top and bottom, as they do in the notes here. Okay. Cool. Now that we have some series that we know converge, we can attempt to do some problems that involve the tests that we have, which are about comparing things. They're all the problems. All right. All right, well, we know that if n is greater than or equal to 1, then n cubed is greater than or equal to n squared. That is the truth. And therefore 1 on n cubed is less than or equal to 1 on n squared. And so by the so we know that this converges. Therefore, this converges as well by comparison. Yay. That was, a pretty stupid example. This one does not converge because the limit of this is not 0. Which is the first thing you have to check. Even if you don't write it down, you have to stare at it and go, is the limit of that 0? Because the limit as n goes to infinity of n plus 1 over n minus 3 is 1. The only limit I know as n goes to infinity is 1 over n. So I would divide the top and the bottom by n. And then as n goes to infinity, that becomes 1 plus 0, 1 minus 0, which is 1, which is not 0. So therefore does not converge. So this sequence converges, but this sum doesn't. Yep.
When we're doing that, we have to prove the sort of definition of sequence convergence without sequence. Converge to 0, or is it enough?
Well, I did this. I proved what the limit was, and the limit isn't 0. Yep.
Yeah, my question is, so you use the 1 on n substitute for those terms, obviously so 0 to the limit. Is that still required? Or do you think we can?
Oh, I mean, you can probably just, I don't know if you're allowed to just, sorry?
Like we can use
Possibly. I don't know what's required or not.
Yeah. I haven't seen that.
Oh, okay. I mean, yeah.
Cool.
It makes me absolutely certain.
Yeah.
What about this one? The limit does actually go to 0. But it's sort of approximately 1 on n. So my instinct is that this does not converge because it's quite close to being a harmonic series. So that would be my first try to try and make this more like a harmonic series. This is my first instinct, to divide it out. Like the numerator almost goes into the denominator. Because if it was just these two, I would cancel them out as they are. So, oh yeah, sorry. If it was just these two, I'd cancel them out as they are. Oops, missed a thing in the chat, sorry. The individual, this bit here by itself as a sequence has to go to 0, has to converge to 0, and that will cause the thing with the sum to converge, which is a different concept. Does that answer your question, Donnie? I said this without the sum sign is a sequence. Oh, crap, sorry. Maybe I was too far away from the thing. How's that? Are we working? Or has my audio gone? Okay, sorry about that. It's too far away from the microphone. This is a sequence when I choose the different values of n, and as a sequence that has to converge to 0 in order for this series to converge. Now, this does go to 0. As n goes to infinity, it'll be approximately 1 on n, which does go to 0, so that's okay, but it still might not converge. And so what I'm trying to do is thinking, well, if when n is close to infinity, it's approximately 1 on n, then that's what I'm wondering about. And so I feel like this is not the best plan, and there is a later test that will work better. But I'm just giving it a go. So this bit divided by this is 1 on root n plus root 3. And this bit divided by this is root 3 plus 1 on n squared minus 3. And this one converges because it's a little bit bigger. Oh, crap. Well, I'm going to have to think about that. It's quite close to 1 on n squared. But technically it's a little bit bigger than 1 on n squared.
Is the issue like addition terms, like really early terms on the other side?
Yeah, it's the wrong way around. Like 1 on n squared minus 3 is technically bigger than 1 on n squared.
Yeah, so that's what stopped you using the comparison test, right?
Yeah.
But obviously as it goes later, it's clearly.
Yeah. 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 So I feel like there's a better comparison test. There are several comparison tests, aren't there? Okay. Donnie, you could divide everything by n squared in order to show that it does convert, that this converges to 0, but that wouldn't be enough to show that the whole series converges. But I could divide by n. Just a second. N plus 1 on n squared minus 3 is the same as 1 plus 1 on n minus 3 on n. That's definitely true. Yeah. If that wasn't there, then this would be, no, I'm just going to look at the other ones. Oh, there's a limit comparison test. So we've got the ordinary comparison test, and there's a limit comparison test as well. That's what we want, because I was looking at it, what happens if it goes towards infinity and comparing it to the other thing? Yes. Okay, so there's the ordinary comparison test, and there's a limit comparison test. So in that case, if an is greater than or equal to 0 and bn is greater than or equal to 0 for all n, and an over bn as a sequence converges, then if Bn converges, then An converges. Which you can apparently prove using earlier tests. And actually something that's useful here is in this hint, it says that if An over Bn goes to C, then An is less than or equal to this times Bn for n large enough. That's really useful. You don't have to show that it's always less than for the comparison test. You just have to show that if there's an n large enough where it becomes less than, and that's okay. Which is a technical detail that he hasn't sort of mentioned, but it is apparently okay. This doesn't really matter what happens in the first 500 terms. It just matters what happens in the infinitely many terms after that. It affects whether the sum goes somewhere. All right, I reckon I can do my thing now. Where was my thing? N minus 3, n minus 1 over n squared, n plus 1 over n squared minus 3. That thing. Okay, cool. Yes, yes. Ah, damn it. It's the wrong way around. This one only proves that things converge. Oh, but contrapositively, if this one diverges, that one would have to diverge as well. Yeah. You want to know which one's on the bottom. So if the top one converges, the bottom one does too in the fraction. Like if the fraction converges and the top one converges, then so does the bottom. But contrapositively, if the fraction converges and the bottom one doesn't, then the top one can't either. Otherwise, the bottom one would have. So we can also say because if An diverges, if Bn converged, then An would converge too, and it doesn't, so Bn can't.
Yeah.
Yeah. No, I haven't used that yet in this, but I was just going. So I was thinking that when n goes to infinity, these 1 and this 3 are very small compared to the n, and so this is going to become 1 on n approximately. And I know that 1 on n doesn't converge. So if I put the 1 on n on the bottom, then it would be okay. So let's do this. N plus 1, n squared minus 3, divided by 1 on n. Okay? And that is the same as n plus 1 over n squared minus 3 times n on 1, which is n squared plus n over n squared minus 3. And if I divide everything by n squared, I get 1 plus 1 on n, 1 minus 3 on n squared. And this converges to 1. So because the fraction of this thing divided by 1 on n goes to 1, that fraction converges. Therefore, if the bottom thing diverges, then so must the top. No. Oh crap, which one's on the bottom? No, I just need to do it the other way around, that's all. It doesn't matter, but like, oh, because if the fraction converges, then the fraction up the other way has to converge too, doesn't it? Not necessarily. Because if it goes to 0, then up the other way it would go to infinity. Okay, so that's important. So the theorem says that if the bottom one converges, then so does the top one. That's what it says, right? Right, and if the top one diverges, then so does the bottom one. So I really should have done this the other way up.
Are we still doing the same question? Is this still the same stuff?
Yeah.
You multiply the whole thing by n over 1.
Yep. I was just trying to compare it to 1 on n.
Okay.
I'm not 100% sure, but I'm just making some of this up. But so if I did it up the other way, then it would have become, damn it. No, we divide the top and bottom by n squared. No, multiply it out. Which does go to 1. So since this converges, and also 1 on n diverges, therefore n plus 1, and that diverges, therefore n plus 1 on n squared minus 3 also diverges by the limit comparison test. And the reason I was wondering if there was another test was I was thinking about what happened to this at the limit. And so I was wondering maybe there's a test that involves doing a limit. Yeah. And so if I compare this to the other one at the limit, then I can tell if one of them diverges or converges. So it seems to be if this fraction converges to a number that isn't 0, then if one of them converges, the other one does too. And if one of them diverges, the other one does too. Sweet. But if it converges to 0, then you really have to be very careful about which way up they are. Sweet. I did real analysis too, and I remember doing like what felt like 20 different comparison limit tests, but I don't remember any of the details. So this is quite eye-opening to me. How are we feeling? So if I was doing this in my own study for this course, which is essentially what I'm doing in front of you, I would be writing them all down, each on a separate piece of paper, so that when I've finished, I could organize them all to compare them to each other and decide for myself which ones go with which situations. But I've already got myself a heuristic which says that if when I look at it and I imagine this limit as I go to infinity, and when I think of this limit as it goes to infinity, it looks similar to like the harmonic series, then this is a decent thing to do. If it looks, when you go to infinity, it's similar to another series does when it goes to infinity, like another series does, then the limit comparison test will work. Yeah. Okay, cool. So a series is absolutely convergent if that, okay. So that's just a definition, it's not really a test. But it does say that if it's absolutely convergent, then it's convergent. Okay, so if the absolute value of it converges, then this converges too. Okay, which is sort of the definition of absolutely convergent. All right. And now we finally have the ratio test. And I'm going to do the ratio test's corollary. So this is the original ratio test, which only applies to things that are positive. But there's a corollary, which is that if they're not already positive, you can absolute value them and it'll work, because that ratchets in the absolute convergence thing. So ratio test says that if an plus 1 over an approaches C and C is less than 1, then an converges. The sum of an converges. C is greater than 1. The sum of an diverges. And if C is equal to 1, go away, I don't want to talk to you. It may or may not converge. And this is proved by essentially comparing your sequence to a geometric, your series to a geometric series. Because if it really was a geometric series, then when you did an plus 1 divided by an, it would be x to the n divided by x to the n plus 1 divided by, just, I do know this one. I know the proof of this one. Just want to, if an was x to the n being a geometric series, then an plus 1 divided by an would be x to the n plus 1 divided by x to the n, which would be x. And if that absolute value is less than 1, then the geometric series converges. And if that absolute value is greater than 1, then the geometric series doesn't converge. We know that. That's the rules for geometric series. So if we want to compare, if we compare our series to the geometric series via the limit comparison test, that's what the ratio test is. Yeah. There you go. So if as you go towards infinity, it behaves similarly to the way a geometric series behaves, then you can just compare it to what the geometric series does. Yeah, which is really cool. I just love it so much. So you could I will tell you something though. This one cannot be done with the ratio test. Because if your terms, the things that you're adding, these terms here, if they are a rational function of n, then when you do an plus 1 over an and do the limit as n goes to infinity, you are guaranteed to get the answer 1, for which the ratio test tells you nothing. So if you have something that is polynomial in n and another polynomial in n, like that. So this is, a polynomial and another polynomial, like this one is. Then when you do the ratio test, an plus 1 over an, like this, and do the limit of that as n goes to infinity, you are guaranteed to get the answer 1. If all of that is an, and it's a rational function, so a polynomial on the top and a polynomial on the bottom, when you do an plus 1 over an and do the limit of that as n goes to infinity, the answer is guaranteed to be 1. And so the ratio test, which doesn't give you an answer when the limit is 1. So do not use the ratio test if it's a rational function. Something to the power of n, that'll be useful, or a factorial will usually be useful too. All rational functions will fit into 3 categories, just while we're at it. You can either have a polynomial over a polynomial where this degree is, let's call this the degree of a, and this degree, no, damn it. So if the numerator degree is greater than the denominator degree, then it will diverge, definitely, because the limit will go to infinity. Like if you've got an n squared on the top and an n on the bottom, it's approximately equal to just n. And so that definitely diverges. If the numerator degree is strictly less than the denominator degree, it's hard to tell. You actually need to, if the numerator degree is 1 less than the denominator degree, it'll diverge because it'll be approximately equal to the harmonic series. So you've got like an n squared on the top and the n cubed on the bottom. It's approximately 1 on n, it'll diverge. So basically, if it's 2 less, then it'll converge.
So even if it's like 1 on like n to the 1.00001, it's converge, right?
Correct.
Yeah. Like 1 to the absolute limit.
Yeah. And if the numerator degree is equal to the denominator degree, then it's going to probably diverge. Well, no, it'll diverge because the limit of the individual terms will go to 1. Like we'll go to a constant and it won't be 0. So yeah, none of that is like theorems. I mean, they're technically theorems. You could write them down and prove them, but it's just an instinct when you've got rational functions to look at that. Yeah. And so when if you have as your thing something that's like n plus 1 over n squared minus 1, 3 to the n over n factorial, when you do that an over n plus 1 over an bit, this bit's just going to go away. It's not going to be part of your decision about whether this converges or not. Because it'll just, the limit of this plus 1 with an n plus 1 and this with an n over will be 1. Yeah, just works out that way every time. I'm sure you can prove that somehow. Okay, that's the ratio test, which tends to be useful for things with factorials or powers, where the n is in the power. N is in the exponent. Let's see if we can find some things that we can now do, right? Oh, well, all right. The limit as n goes to infinity of minus 1 to the n times n over n plus 1 is the limit as n goes to infinity of minus 1 to the n times 1 over 1 plus 1 on n, if I divide the top and bottom by n, and that doesn't exist. Yeah, and I mean, even better, the absolute value of this, like if an is equal to this, the absolute value of an is n over n plus 1, which goes to 1 as n goes to infinity, which is not 0, and therefore the sum of an diverges, and therefore the sum of the absolute value of an diverges, therefore the sum of an diverges. That's probably the full version of the proof. It does, but this is the contrapositive of it. If the absolute value one converges, then the non-absolute value one does too. Therefore, if the non-absolute, oh crap, you're right. Tell me, where does it go? Oh crap, it works the other way. That was such a good idea. The proof still works, yeah. This original limit doesn't actually exist because the limit of 1 minus 1 to the n doesn't. So, because it's always 1 or minus 1 and doesn't go to any one particular number. There is no number that it's close to all the time. From the definition of what limit means with the epsilons and the deltas. Epsilons and the n's, sorry, wrong limit. Yeah. Oh crap, that was such a good idea. So basically, just a second. So if this diverges, that can't converge, because if it did, this would. Okay, yeah, contrapositive. Okay. Right. But it's much more common for the absolute one to not converge and the one that's got pluses and minuses to converge. Like that's a thing that can happen. And the alternating harmonic series does that. Okay. All right, so this was a bad proof. Sorry about that. Good-o. All right. Yeah, okay. The absolute value of the alternating harmonic series doesn't converge, but the alternating harmonic series does anyway. And so, yeah, okay, that's right. Okay. What other tests have we got? Oh, no, these aren't tests. These are the questions. No wonder they look like questions. Okay. Yep. Oh, there's a root test as well. So the root test says an is greater than or equal to 0, and an to the power of 1 on n goes to c, then c equals, if c is less than 1 means converge, c is greater than 1 means diverge, and c is equal to 1 means nothing. Okay, that's my root test. Beautiful. So this is literally, this doesn't compare it to another series, does it? That's cool. Okay, cool. So when would that be useful? So if it had a power of n, then that would.
Yeah.
Yeah, though technically you use the geometric series to prove this, but yes. But it matches up with the geometric series converging. Okay, cool. Right. This is very specialized. I'm not sure where this would.
It is comparison to geometric series.
Yeah. You're technically not allowed to use the root test to show that the geometric series converges because you use the geometric series to show that the root test works. It's a little bit like you're not allowed to use L'Hopital's rule to show the fundamental trig limit. Because you use the fundamental trig limit to do the derivative of sine, and so there, which is what L'Hopital's rule uses. So it's circular reasoning. It works, but it's just because it's supposed to. It's a little bit like using an ohm meter to prove Ohm's law. It's like machine built using Ohm's law confirms Ohm's law. So, okay, anyway. So, and then there's the alternating series test. So if we've got that an is decreasing positive, and obviously you definitely need the an to go to 0 because you always need that, then this yn plus 1, why does it matter? Then that converges. You can put an n plus 1 up there if you want, but it doesn't really matter. It's just minus the other one. So, yeah. And remember, so this is something that's actually technically in Maths 1B. We finally got to another one that was in Maths 1B. And in Maths 1B, this test says it doesn't an doesn't have to be decreasing everywhere. It just has to be eventually come to a point where it's decreasing after that. Because this whole series stuff, whether it converges, it doesn't matter what happens for the first finite number of terms. So you don't have to worry about it being decreasing all the time. It just has to decrease eventually. Oh, no, it means that an is positive and decreasing.
Oh, okay, yeah.
Yep, this is the classic proof that for the alternating harmonic series converging. It's like, well, the individual terms are decreasing. 1 over n plus 1 is less than 1 over n. And they do go to 0, and it alternates between plus and minus. So ta-da, alternating series test. And the proof is apparently, oh wow. So that's why he put that proposition in before. That's cool. So if you make a new series out of if you make a new sequence out of these things, such that you have just every second one in one sequence and every second one in the other, and you add those two things separately as serieses. So Theorem 3.16 said that if you had, oh wow, No, it's not. Ignore that. It doesn't matter. That's so cool. Like the proof of it. Just I love it. I haven't read the details. I just love this move here where you can, because it keeps getting alternating between adding a bit and subtracting a bit, you can show that if the first one's positive and then you add a negative number, then the second one will be below it. And then the third one has to be more than it. But because the terms are decreasing, you don't get all the way back up to S1. And so you go back and forth like this, and you get this sequence of the even ones and this sequence of the odd ones. And then whatever the actual SN will be squeezed between them. And so because of the squeeze law, the SN has a limit, which is really cool. So I just love it so much. And so this is actually proved using the original definition of what converging for series means. Wow, that's cool. That's so exciting. So I just, yeah, anyway. So now we have another series that we know, the alternating harmonic series, that goes on our list. If you're not asked to prove it, you're allowed to just say it converges. And then we've got rearrangements, but who cares? That's too hard to talk about. And that's it. That's the last one. So let's organize these. So this, the alternating series test and the root test and the ratio test, all are about just the series itself and its own terms, and don't talk about a different series at the time. You do a calculation based on the terms you've got, and it helps you make a decision about whether it converges. This one and this one, like the limit comparison and the definition of absolute convergence, are comparing two series to each other. So there are some tests that compare two series and some tests that just use the series that you have. So let's just see. Technically, the definition of convergence just uses the series itself. This one just uses the series itself as well, just the individual terms going to 0. Okay. Yep, so there's only two that are about comparison, which is the comparison test and the limit comparison test. Sorry? Oh yes, and the absolute value one. They all compare it to a different series. But the rest of them, well, and this one is built out of other series. That's technically separate other things. So that's one way of classifying. Does it tell you about convergence because you know about other series, or does it tell you about convergence because you have done something to the series you've got? And that's a useful way of classifying them. Yeah, so if I was teaching real analysis, I would build those, I would do that as I went. Oh, yes, that'd be so cool. I love organizing things. It's the best way of understanding them. You've got to decide how they're similar and how they're different. Because if you want to know situations to use things, you need to know how they're similar and how they're different. You have to be able to tell the situations apart. And then on a whole separate list, there's a list of ones that you know, and they're the ones that you have to use to do the comparison tests. Because you have to compare it to something that you know converges or diverges. Right. So because any multiple of a series, if a series converges and any multiple of it does as well, then you don't actually need to compare it to the original series. You just need to compare it to some multiple of the original series. Sorry? Oh, it might be. I don't know. I'm just thinking about stuff. Yeah. And multiplying something by n makes it bigger if n is a natural number. Like if you've got an, right, and this converges, or even if it doesn't, nan is guaranteed to be greater than or equal to an, because n is more than or equal to 1. So if multiplying it by n turns it into a series that you like, then you might be able to do
By n, do you mean like the n that's been iterated over? Or
Yeah,
like a constant?
the n that's been iterated over.
Is there a, that would make it diverge, right?
Sorry, only if this one diverges that make this one diverge.
No, hang on. If one of AN is one on n.
No, I was just no, but doesn't matter. But it's like if you have AN and you definitely know this. So therefore, if this converges, then so does that.
Oh, yeah.
And if this diverges, then so does that.
Yeah.
And so as a comparison test, you could use that, right? Yes, and we already used it with the n cubed and the n squared. Like that's cool. But I was just thinking about things.
It's like linear comparison with like dividing by one on n.
Basically. But it just might be easier to process in your own mind. That's all. But something you've noticed there and just said is that the different tests can be each other in different contexts. Yeah. And that makes sense because a lot of them, like each new test uses an old test to prove itself.
Yeah, it won't be a science to do a diagram and show like which stuff you need to show, like which tests you need to show in other tests. But like the whole course, like another which proves
All right. How are we feeling? It's actually, oh wow, it's the time. Okay. Well, thanks for letting me be here and do this. I've learned a few things about real analysis. I'm hoping it was helpful. Don't forget, Maths Learning Centre is open Monday to Friday, 10 a.m. to 4 p.m, all the way to the end of the exam period. I don't know when your exam is. Okay, I'm just going to stop the recording.